you're looking at what is arguably the most successful theory in the entire history of physics. And the amazing thing is, it can all be written down in a single, well, pretty massive equation. Today, we're going on a tour of that very equation, the Standard Model Lagrangian. So, let's dive in.
So here it is, in all its chaotic glory. I know. It looks like an absolute mess of symbols and scribbles, doesn't it? It's definitely not short, and it is certainly not simple. But this one equation holds our best understanding of the entire subatomic world. And believe it or not, we're going to walk through this thing piece by piece.
Now, you've probably seen this one, right? E equals mc squared. It's famous because it's short, it's elegant, and it fits perfectly on a coffee mug. Yeah, you'd need a pretty giant mug for our equation. And yet this complex beast is way more fundamental than E squared when it comes to understanding how the universe really works at the tiniest scales.
Okay, so how in the world are we going to tackle this thing? Don't worry, we'll break it down into 5 simple steps. First up, we'll talk about why it's considered the universe's most important equation. Then we'll get into why it looks the way it does by exploring nature's path of least action. After that, we'll meet the players, matter and force. Then it's the main event, our guided tour of reality. And finally, we'll look at the big picture with the equation's unsolved mysteries.
All right, let's get into it. Part 1, the universe's most important equation. Let's start by just appreciating how incredibly powerful this theory actually is.
Now, that might sound like a pretty bold claim, but it's totally true. So why is it the most successful? Because its predictions match up with real-world experiments with a precision that is just unmatched in any other field of science. For instance, it predicts a property of the electron, its magnetic moment, to an accuracy of 1 part in a trillion. To give you an idea of what that means, that's like measuring the distance from Los Angeles to New York City and being off by less than the width of a single human hair. All of that incredible predictive power is packed right into the equation we're looking at today.
Okay, so that's what it does. But why does it look so complicated? That brings us to part 2, nature's path of least action.
You know, it all starts with this really beautiful idea called symmetry. In physics, all this means is that the laws of nature don't change just because you change your point of view. And here's the wild part. These symmetries are what actually give birth to the fundamental forces. For example, if you demand that the math describing a particle works out perfectly, no matter how you look at it, you're actually forced to invent the electromagnetic field just to make everything balance out. It's just an incredible, profound idea.
So the main tool we use to write all this down is called the Lagrangian. The easiest way to think of it is like a master formula, or a recipe that summarizes everything a system can do. For something really simple, like a ball flying through the air, it's just its kinetic energy. That's the energy of motion minus its potential energy.
And the reason the Lagrangian is so powerful is because of something called the principle of least action. It basically says that nature's kind of lazy. Things will always take the path of least resistance. So it's like a 3-step process. First, you write down the Lagrangian for whatever you're studying. Second, you apply this principle. And third, the math just spits out the exact equations for how that system is going to behave.
All right, part 3. Before we dive into the equation itself, we need to meet the players. I like to think of them as the universe's 2 teams, matter and force.
So the Standard Model splits all particles into 2 families. On one side, you've got your fermions. This is the stuff of the universe, the electrons, the quarks, everything that makes up you, me, and this planet. And on the other side, you've got bosons. These are the force carriers, like the photon that carries light. So you can think of one team as the bricks, and the other team as the mortar holding it all together.
Okay, you've been patient. It's time for the main event, part 4, our guided tour of reality. Let's actually read this thing together. Let's start with this first big chunk right here. You see all those F's? This is the part of the equation that's all about the forces themselves. The electromagnetic force, the weak, and the strong nuclear forces. You know, if this was the only part of the equation, you'd have a really bizarre universe. One filled with energy and light, but with absolutely no physical stuff in it at all.
So this part of the equation tells us everything about those force-carrying particles, the bosons. It tells us how they move, how much energy they have, and, this is really important, how they can interact with each other. For example, the gluons that carry the strong force can actually stick to one another. This is the term that describes that behavior. Well, a universe with just forces is kind of boring, right? It's pretty empty. So let's add some stuff. That's what this next section does, the one with the Greek letter psi. This is where we add the ingredients for matter into our cosmic recipe. This is the real magic. This is where matter and forces actually connect.
This term doesn't just describe the matter particles themselves. It has all the rules for how they're supposed to interact with the forces. This is what tells an electron how to feel a magnetic field. It's how our two teams, matter and force, actually talk to each other.
Now, you might have been looking at this and noticed this weird little HC tucked away at the end. What in the world could that stand for? Well, this is one of those spots where quantum physics gets a little quirky.
The official physicsy answer is Hermitian conjugate. It's basically a fancy math instruction that says, hey, add a mirror image of the term that came before this. It's a clever trick to make sure our calculations make sense. But, there's a running joke among physicists that what it really stands for is hot coffee, because this is usually the point in the calculation where you really need to take a break.
All right, after our coffee break, let's look at the final piece of our equation, highlighted right here. So far, we've got forces and we've got matter, but we have a huge problem. In our theory so far, every single particle has zero mass, and that's obviously not right, so we need to fix it.
And this, of course, is where the legendary Higgs field comes into play. These final terms describe the Higgs field and how it interacts with other particles to give them mass. This is the part that explains why an electron has the mass it does, and it's also the part that predicted the existence of the Higgs boson, the particle that was famously discovered at the Large Hadron Collider.
And just like that, we've walked through the whole thing, which brings us to our final part, the equation's unsolved mysteries. Because as incredible as this thing is, it's an unfinished masterpiece.
For all its amazing power, there are these huge, gaping holes in what the standard model can tell us. It says absolutely nothing about gravity. It can't explain the enormous mysteries of dark matter and dark energy. It doesn't tell us why there's so much more matter than antimatter in the universe. It doesn't even tell us why particles have the masses they do. We just have to measure them and plug the numbers in by hand.
So even though the standard model Lagrangian is this just insane victory for science, it's not exactly pretty, is it? A lot of physicists feel that the true final theory of everything, if it exists, ought to be simpler, more elegant, something you could actually fit on a coffee mug. And that search for a deeper, simpler truth continues.
Right now, this equation works with breathtaking accuracy. So much so that physicists are having a really hard time finding any situation where it fails. But they keep looking. They keep pushing it, testing it, searching for a crack. Because they know that in that first tiny glitch, that's where the clue to the next great discovery is hiding. So the real question is, what glitch in this equation will lead us there?